Hello everyone. Today we will be starting with session 7 of coordination compounds. Previously we were discussing the geometrical isomerism for square planar complexes, and now we will be starting with that of octahedral complexes. Students are requested to drop down their names for attendance purpose. We will be starting in a while. Okay, so let us start now. See, we have to do the geometrical isomerism, right? There were two types of isomerism that we need to discuss. That is the geometrical isomerism and the optical isomerism, right? Which come under stereoisomerism, in which the connectivity does not change. And one was structural isomerism. The structural isomerism had that isomers in which the connectivity between the atoms were changing. But in stereoisomerism, only the spatial arrangement changes, right? So there are two types of stereoisomerism. One is geometrical and one is optical. So we were discussing about the geometrical isomerism. It is due to the different arrangement of ligands around the central metal atom, right? So previously we studied that tetrahedral complexes do not show any kind of geometrical isomerism. That means the number of geometrical isomers for tetrahedral complexes come out to be 0. While in case of square planar, we have discussed the geometrical isomerisms for unidentate ligand also, and for symmetrical and unsymmetrical bidentate ligand also, right? That were the chelating agents or chelating ligands, right? Now we need to focus upon octahedral. Trigonal bipyramidal are not in our syllabus, so we will discuss about octahedral today. See, first in octahedral complexes, first we need to define that what are the angles between the different ligands. For example, here 1 and 6 are having an angle of 180 degree. 2 and 4 will be having an angle of 180 degree, and 5 and 3 will be having an angle of 180 degree, right? This you need to remember that in case of trans, the angle is 180 degree, while in case of cis, you will have the angle as 90 degree, right? So these are the trans ones. That means 1 and 6 are trans to each other, 2 and 4 are trans to each other, and 5 and 3 are trans to each other. While the remaining angles, for example, the angle between 1, 2, 5, 4 and 3. That means the angle between 1 and 2, 1 and 5, 1 and 4 and 1 and 3 is 90 degree. That means these ligands are cis amongst themselves, right? While with 6 you are having 3, 4, 2 and 5. The angle comes out to be 90 degree and these ligands are cis to each other, right? So this much you need to remember. In the previous session also, I discussed a trick with you that the isomers in which at least one angle should be changed, that will be the geometrical isomer to each other, right? For example, let us say that we are having this octahedral complex and another one I draw it like this. For example, I place 2 and 5 like this, right? 1, 5 like this, 3, 4, 1 and 6. Now here I have changed the position of the ligands, right? So it comes under stereoisomer because I have not changed the connectivity of the atom. I have only changed the arrangement of the ligands around the central metal atom. Okay. Now what is happening here is, see, here 1 and 6 were 180 degree, here also 1 and 6 are 180 degree. Here 2 and 5 are 90 degree to each other. While here 2 and 5 are 180 degree to each other. That means one angle is changing. right? And if at least one of the angle is changing, then these both will be geometrical isomers to each other. These will be geometrical isomers to each other. Suppose I draw another complex like this, let us say, and changing the positions. Here I keep 2, here I keep 4, here I keep 3, and here 5, 1, and then 6. Now you compare the angle. Angle between 1 and 6 is 180 degree, here also 180 degree. 3 and 5 is 180 degree, here also 180 degree. 2 and 4 are 180 degree, here also 2 and 4 are 180 degree. 2 and 3 are 90 degree, 2 and 3 are 90 degree. 4 and 5 are 4 and 5 are 90 degree, 4 and 5 are 90 degree. 4 and 3 are 90 degree, 4 and 3 are 90 degree. 2 and 5 are 90 degree, 2 and 5 are 90 degree. So that means all the angles of the first arrangement and the third arrangement are same. Therefore, they are identical. They are not geometrical isomers, rather they are identical. Right? This is another way of drawing the same isomer. So this is how you can identify that which one is a geometrical isomer and which one is the identical complex. Okay. Is it clear? Now, see, now the possible complexes of octahedral are that all the ligands are same. Remember here, A, B, C, D, E and F are monodentate ligands or unidentate ligands. They are monodentate ligands. Okay, that means the donation is from one site only. So possible complexes are Ma6, Ma5B, Ma4B2, Ma4BC, Ma3B3, Ma3B2C, Ma3BCD, Ma2B2C2, Ma2B2CD, Ma2BCDE, MABCDEF. That means from starting to all the 6 ligands being the same, here we are ending with all the 6 ligands are different. Right, so different geometrical isomers will be possible for these complexes. However, we need to focus upon a few only. Okay, so these are the possible complexes in which only one one type of ligand, that means the monodentate ligand, is present. Here all the ligands are monodentate in nature. Okay. Now second one is when ligands are bidentate, symmetrical and monodentate type. That means the ligand can be monodentate and they can be bidentate but symmetrical. That means let us say you are having ethylene diamine NH2 CH2 CH2 NH2. So here you were having bidentate symmetrical because you can see that both the donor atoms are the same, right? NH2 NH2. This is a symmetrical bidentate ligand. So you will write it as AA. AA means that it is a symmetrical bidentate ligand. Okay, so these are the possible complexes that you can have when you are having bidentate symmetrical ligand and monodentate type ligand. So here 3 are a bidentate symmetrical ligand, 2 are bidentate symmetrical, 2 are monodentate, 2 are bidentate symmetrical, A and B are monodentate, 1 is bidentate symmetrical, 4 are monodentate. Similarly for other complexes also, right? Now next one is, let us say you are having unsymmetrical bidentate ligand. For example, let us say you are having glycine NH2 CH2 C double bond OO, right? You are having glycine. Now you are having unsymmetrical bidentate ligand. Donor atoms basically are not the same, so you can write it as AB, right? So this also involves various type of complexes in which 3 of them can be unsymmetrical bidentate, 2 of them can be unsymmetrical bidentate, right? Or 1 of them be unsymmetrical bidentate, and so on. Okay, now we need to discuss or focus upon only few complexes. First one is, for example, you are having Ma2B4, right? Where A and B are basically what? Monodentate ligands, right? So example is, here you are having cobalt NH3 4 and then Cl2 positive. This is your complex. So it can be written as cobalt is M, this is A2 is Cl2, and B4 is NH3. Right? So this kind of complex you are having. Now here two isomers are possible, cis and trans. Now if you compare it, see here that Cl and Cl are 90 degree to each other in one, and here Cl and Cl are 180 degree to each other in the second one. So I already told you the ligands which are oriented at 90 degree will be cis to each other, while the ligands which are orientated with an angle of 180 degree towards each other, they will be trans in nature, right? So one geometrical isomer will be cis and the other one will be trans. So how many geometrical isomers for Ma2B4 are possible? Two geometrical isomers are possible. Okay. One is where A is cis to each other and one is where AA is trans to each other. Next one you come across is MAA2A2, where AA is what? The symmetrical bidentate ligand, for example ethylene diamine, and A2 is the monodentate ligand, two monodentate ligand. Here also you can have two A's as cis to each other and two A's as trans to each other. The example is cobalt En2 Cl2, this complex you are having, right? So 2Cl can be cis to each other and 2Cl can be trans to each other. So here you can see the angle is what? 90 degree. Here you can see that the angle is what? 180 degree. Let us see that how will you draw the complex. Cobalt you are having, right? Ethylene diamine is what? NH2, then CH2, then CH2, and then NH2 again. Here also you can have NH2, CH2, CH2, and then NH2. And then you can have chlorine and chlorine here. Basically, it is an octahedral complex. So you can have two possibilities. Either you place 2Cl at 90 degree or you place 2Cl at 180 degree. So two geometrical isomers are possible for this type of complex, that is cis and trans. Now next one is very important from the examination point of view, Ma3B3 type complex. Right. Now these show different isomers which are given a special name, that is the facial and the meridional. Wherever you are seeing a complex like this, that Ma3B3, in which A and B are monodentate ligands, you can have two isomers, that is facial isomers and the meridional isomer, if you are talking about geometrical isomerism only. Okay, so two geometrical isomers for that are possible. One is facial and second one is the meridional. Now what is the difference between facial and meridional? Let us see that. See, facial is when that same type of ligand are 90 degree to each other. For example, let us say you are having cobalt NH3 3 NO2 3, right? So all the NH3s should be 90 degree to each other. They should not have an angle of 180 degree. And all the NO2s should be at 90 degree to each other. They should not have an angle of 180 degree. So here you can see, if I mark this as NH31, NH32 and NH33, right? So 1 and 2 have 90 degree angle, 1 and 3 have 90 degree angle, and 2 and 3 are 90 degree angles. So the same type of ligands are having an angle of 90 degree between each other. Therefore, it is a facial isomer. While in case of meridional, it is reverse. That even if one of the angle becomes 180 degree, then it becomes meridional isomer. For example, let us say we are having 1, 2, 3. Now here 1 and 3 are having 180 degree, right? 1 and 2 are 90 degree. 3 and 2 are 90 degree. But even if one angle is 180 degree between the same ligand, then it becomes the meridional isomer. And it is possible in only complexes like Ma3B3, right? Or you can also define in this way, that if the trio of donor atoms, that means the three same donor atoms or three same donor ligands, occupy adjacent position at the corner of an octahedral face. See here that they are occupying the adjacent position, then it is known as facial, right? While when the positions are around the meridian of the octahedron, we have meridional isomer. I have So basically, this is the theoretical part. If someone asks you that what is a facial, what is a meridional, then you can write down the definitions like these. But if you want to identify that which one is a facial and which one is a meridional, use that trick that if all the angles are 90 degree between the same ligands, then it is a facial, otherwise it is a meridional isomer. Okay. Now next, here is a question. Which type of isomerism may be shown by the complex? You are given the complex. So amongst A, B, C, D, which one should be the answer? Anyone with the answer for this question? Here you are given a complex of ruthenium. This is the ionization sphere. This is the coordination sphere. You have to tell me that which type of isomerism is shown here by this complex. Ionization, linkage, geometrical, or all of these. Okay. What about others? Charm has given the answer as D. What about others? See, ionization isomerism can be shown. Water can be outside also, or S2O3 can be outside also, and NO3 can be inside also, right? So it can show ionization isomerism. In case of linkage isomerism, you can see here that S2O3, it can donate from sulfur also and it can donate from oxygen also. So it can show linkage isomerism also. Now the third one is geometrical isomerism. It can show geometrical isomerism also. We can have this complex as Ma4BC, right? So either B and C can be 90 degree to each other, or B and C can be 180 degree to each other. For example, like this, Ma4BC. One geometrical isomer will be this when they are 180 degree to each other, B and C, and one can be this when they are 90 degree to each other. So two geometrical isomers can be possible for this, right? So it can show geometrical isomerism also. So the answer will be all of these. Yes, you both are correct with your answers. Good. Now next is optical isomerism, right? So what is optical isomerism here? Optical isomers are those isomers which are mirror images that cannot be superimposed on one another. I hope this you have learnt in your organic chemistry also, right? We are having that in nucleophilic substitution part, alkyl halide and aryl halide chapter. We are having this. So optical isomers are mirror images that cannot be superimposed on one another, and they are called as enantiomers, right? So enantiomers are what? Basically mirror images that cannot be superimposed on one another. Now the molecules or ions that cannot be superimposed are called chiral in nature, right? And the ones which can be superimposed on one another, they are known as achiral, right? Or they are also known as optically active, and achiral are known as optically inactive. Now, optical isomers basically have two forms, that is the dextrorotatory and the levorotatory. Depending upon the direction they rotate the plane polarized light, right? For example, you are having here unpolarized light from the light source. Now you make it polarized by a polarizer. right? Now here is the sample tube containing the organic molecules. So if this sample rotates the plane polarized light by uh, in the right direction, then it is dextrorotatory. Otherwise, if he rotates the plane polarized light in the left hand direction, then it is leviorotatory, right? So D and L means what? D stands for dextrorotatory and L stands for leviorotatory. Now coming on to the optical isomerism, we have to study for, let us say, tetrahedral, right? So tetrahedral, we are having MABCD type complex in which the ABCD are monodentate ligands, right? So here if you draw the mirror images, let us say that we are having a mirror here, right? Now if you look at the mirror, D will be like this, C will be towards this, A will be this, and B will have a mirror image like this. Now this cannot be superimposed on this, right? This cannot be superimposed on this. So therefore they are optical isomers to each other. Or the other way in which you can find out that a particular complex is optically active or not is to find out a plane of symmetry. A plane of symmetry. If the complex is having a plane of symmetry, then it will be optically inactive. That means it will not have optical isomer, right? While if the plane of symmetry is absent, then it will be optically active. Then the complex will be optically active. So here there is no plane of symmetry, therefore the complex mirror image will not be superimposing on it, and therefore it is having a optical isomer, right? So the one pair will be dextrorotatory and the one pair will be the leviorotatory, right? If symmetrical bidentate ligand are present, symmetrical bidentate like ethylene diamine you can have, or oxalate you can have, or acetyl acetonate you can have, right? If there is a symmetrical bidentate ligand in which no chiral center is present, then the complexes are optically inactive. For example, let us say that we are having beryllium oxalate. So oxalate is what? A symmetrical bidentate ligand, and also it is not having a chiral center, therefore it is inactive because plane of symmetry will pass through it. Similarly for zinc acetyl acetone also, that it will have a plane of symmetry passing through it, therefore it will also be inactive optically, right? Now next, tetrahedral with unsymmetrical bidentate ligand will be optically active. For example, let us say that we are having metal here, right? Unsymmetrical bidentate ligand we are having. So draw a tetrahedral structure first. 1, 2, 3, 4, somewhat like this, right? So A and B, let us say we are having unsymmetrical here and then unsymmetrical here. Because the plane of symmetry is not there, therefore it will be optically active, right? Example is zinc glycinato 2, and here also if you will take this in a tetrahedral manner, it will also be optically active. No plane of symmetry is passing, therefore they will be optically active. Okay. Now, optical isomerism in chelated tetrahedral and square planar complexes is also observed. So here you can see that optical isomer in chelated tetrahedral will be shown when there is an unsymmetrical bidentate ligand, right? And square planar complexes, if you will have, because they have a plane like this. For example, let us say you are having this A, B, C, D, right? You can cut it like this in the plane only, right? You can slide it like this, so the two halves will be reflecting each other. So this type of square planar complex, it will be optically inactive. While in case of a chelating ligand, the square planar complexes may exhibit optical isomerism. Okay, so this you need to remember. First point is what? That tetrahedral complexes of the type MABCD has optically activity, right? If symmetrical bidentate ligands are present, which are having no chiral center, then the complexes are optically inactive, and the tetrahedral with unsymmetrical bidentate ligand, they will be optically active. Okay. Now, in octahedral complex, the optical isomerism is more common and is more important for octahedral complexes. For example, we are having cobalt ethylene diamine 3, right? This complex we are having. So, here if you draw the structure like this, you will find that no plane of symmetry is passing through this, right? Don't imagine like this that it is not present in the plane of the paper, right? If you look at the video, see here that one is present like this, one axial one is present like this, one is present below, and the four are present here, right? So you have to imagine like this, and when you make like this, for example, I'll draw it for you, and one will be below, right? And the four will be like this, 3 and 4. Okay, so here if you draw, this will be En, that means this one and this one will be connecting, right? So this will be ethylene diamine. Similarly, here and here, so this and the next one, here will be the ethylene diamine, and here will be another ethylene diamine. So they will have no plane of symmetry because this compound is not having any plane of symmetry. Therefore, it will have a optical isomer. That means the mirror image of this compound will not be superimposable on it. If you draw the mirror image, you can see here the mirror image is this. If you place the mirror like this is the mirror. Okay, so this mirror image is not superimposable on this, right? You cannot superimpose like this, because if you will tend to superimpose, this En will come here, this En will come here, and this En will come here. That means the mirror image is not superimposing on each other. Therefore, these are optically active, and these both are optical isomers, right? So one of them will be D and one of them will be L. That means one of them will be dextrorotatory and the other one will be the levorotatory. Now next is Ma2B2C2 type complex, right? So here if you draw the mirror image, Ma2B2, here cobalt is M, A2 is pyridine, let us say, B2 is Cl, and C2 is NH3, right? So we have drawn the octahedral complex like this. Now here you can see that pyridine and pyridine are 90 degree to each other, Cl and Cl are 90 degree to each other, and ammonia are 90 degree to each other. That means it is a cis type of complex, right? This is a cis type of complex. So now if you draw the mirror image of this pyridine will come here, this pyridine will come here, Cl will be away, then Cl will be away, and this ammonia will be reflected here. Now, if you come to superimpose this on its mirror image, you can see here that here it is Cl, while here it is NH3. If you will superimpose, here NH3 will come. That means the mirror images are not superimposable on each other. However, you can also turn the mirror image, right? You can also rotate it like this, but you cannot flip the compound. This you need to remember, that you can, for example, let us say this is a mirror image. I can rotate it like this to make it superimpose on the real image or the complex, the first complex, but I cannot flip it, right? I cannot flip it out of the plane, rather I can rotate it. But here also, on rotation also, you can find out that the mirror image is not superimposable on the first one, and therefore they both are optical isomers to each other, right? Also, you can find out one through the trick also, that plane of symmetry will not be passing through this complex. Here, if you draw the plane of symmetry, Cl will be reflecting ammonia, right? So this is not having plane of symmetry. Here, if you draw, pyridine and ammonia will be reflecting. So this is also not a plane of symmetry, right? So either way you try to draw the plane of symmetry, that you will not find out any plane of symmetry in this compound. So it will be optically active. Okay, it will have optical isomer. Now next is this Let us say we are having COEN2 Cl2. So two possible geometrical isomers are there for this, as we have already discussed. One is the trans one and one is the cis one. This is the trans one. So if you come on to the trans one, let us say it is having a plane of symmetry. If I cut it like this, let us say, if I cut it like this, so En and En will be reflecting each other, right? And Cl and Cl will be cutted like this, so En and En will be reflecting each other. So that means if the plane of symmetry is passing through the trans isomer, that means it is optically inactive. That means its mirror image will be superimposable on this, right? So it is optically inactive. It will not have a optical isomer. Coming on to the cis one, you can draw the cis isomer like this, right? So looking at the diagram, you will see that here you can draw a plane of symmetry, but no, this compound is not present in the plane of the paper, right? If you draw the octahedral, try to hold pens in a octahedral shape, you will find out that one En will be like this, one ethylene diamine will be like this, right? And one will be like this. So they will not be reflecting each other, right? Therefore, it is optically active because no plane of symmetry is present here. Do not imagine two ethylene diamine to be in the plane of the paper, as we are having this ethylene, this axial bond and one this equatorial bond. We are having one ethylene diamine like this and the downward axial bond and one here. So this will be having ethylene diamine like this, right? So they both will not be reflecting each other when you draw a plane of symmetry like this. Therefore, we are having no plane of symmetry in this complex and it is optically active. Okay. For the cis isomer, if you say one optical isomer is present for it, but for the trans isomer, because there is a plane of symmetry passing through it, therefore we can have no optical isomer for the transgeometrical isomer. Right? Question: out of the following two coordination entities, which one is chiral? Which one is optically active? See, Sham, when you were drawing cobalt En3, let us say, this we are having NH2 and this bond we are having NH2. Then this we are having NH2 and then NH2, and then this we are having as NH2 and then NH2. If you draw the mirror image of it, it will be somewhat like this: NH2, NH2, then here it will be NH2, NH2, and then here it will be somewhat like this: NH2, NH2. Now if you superimpose on it, right? For example, let us say these are my two hands. If I superimpose this, this is my mirror image, right? This hand is the mirror image of this. If I superimpose on it, the two thumbs are not superimposing. Rather, the fingers are also not superimposing on each other. So therefore, our two hands are what? Optical isomers to each other. Similarly, here also, if you try to superimpose this, let us say this is B and this is A. So if you try to superimpose B on A, this NH2 NH2 part will come here, somewhere here, right? And this NH2 NH2 part will come somewhat here. And this NH2 NH2 part will come somewhat here. So basically the two are not superimposing on each other. Therefore they are optical isomers to each other. Now give the answer for this question. Out of the following two coordination entities, which one is optically active? I'll draw the structures for you. One is cis. This will be somewhat like this, Cl. And then you will be having oxalate here, oxygen, oxygen. and here you will be having oxalate. Yeah, this is the cis isomer and this one is the trans isomer. Cl, Cl, oxalate here, and let us say oxalate here, both having oxygen atom. Because what is oxalate? C double bond O, O negative, and C double bond O, O negative. So these act as a donor atom, right? So C double bond O, I am not showing. This is incorporated in the ring only. Now you tell me which one is optically active. Which one will have a optical isomer? You can remember that the one which will be having plane of symmetry will be optically inactive. If plane of symmetry is present, it will be optically inactive. And if the plane of symmetry is absent, it will be optically active. Anyone with the answer? Anyone with the answer? Which one is optically active and which one is not optically active? You can find out using plane of symmetry. If there is a plane of symmetry passing, then it is optically inactive, and if there is no plane of symmetry, then it is optically active. Just now we have discussed. Anyone with the answer? Or other way around, you can draw the mirror image of both and find out if their mirror images are superimposable or not. Okay. It is asking optically active, not inactive. I'll show you by both the methods. See, plane of symmetry, here it is not passing, right, anywhere. Here the plane of symmetry is not present, right? So this will be optically active. And here if you see, a plane of symmetry is present. If I cut this molecule like this through Cl and Cl, oxalate and oxalate will be reflecting each other. So this is optically inactive, right? You can just a second, I'll rub this part. You can find out using the mirror technique also, right? For example, you draw the mirror image of this. This will come out to be what? Cl here, Cl here, then here, then this one will be here. Now this is not superimposable on this. See, Cl will come here, right? It should come here rather. So this is optically active. But if you draw the trans one, so trans one will be like this. Draw the mirror image. Oxalate, oxalate. Now if you superimpose on this, see, this part will come here, this part will come here, this Cl will come over this, and this Cl will come over this, right? So this will be optically inactive. So the answer is A. So you can say that cis isomer exists as two optical isomers while the trans one is optically inactive. Okay, yes Arun, you are correct with the answer. Good. Now see, I have explained all the important complexes for which you need to basically learn for your exam point of view, right? For which you need to learn the geometrical and the optical isomers for the examination point of view. Because there are many of the complexes that are possible, right? Either one way is to use that trick in which at least one of the angle will be different. That will be geometrical isomer, and the second one is you can use the plane of symmetry or the mirror method to find out the optical isomers. Or the other way is that you can just learn this table, right? You can also learn this table. Basically, we have done all the important compounds which are previously asked in the JE or the NEET pattern. That we have done. I have explained you in detail. But even if you want to extend that, you don't want to miss out on anything, then you can learn this table, or you can use the method, like you can use the angle method for the geometrical isomers, and you can use the plane of symmetry or the mirror method for the optical isomers. Okay, you can practice these at home, right? But the important ones are placed in the red box. For example, Ma4B2, it is optically inactive, right? Number of possible geometrical isomers are 2. See here, if in the question it is asked that define the number of stereoisomers, then you have to include geometrical isomers also and optical isomers also. If it is specifically asking you that determine the number of geometrical isomer, then only consider geometrical isomer, do not include optical isomers in it. Okay. Similarly, for Ma3B3, we have learned two isomers, facial and meridional, right? And here also both are optically inactive. Then for Ma2B2C2, the number of possible geometrical isomers are 5, and out of which one is optically active, right? So number of enantiomer pairs will be 1. So a total of 6 stereoisomers are possible. Okay, for this complex in which all the ligands are different, all are monodentate and all are different, you are having possible number of stereoisomers as 30. So either you can remember this table as such, right? Each and every complex and find out the number of geometrical isomers through the angle method and the optical isomers through the plane of symmetry. Now next one is this MAA3 and MAA2A2. This we have already done, that possible number of geometrical isomers are 1, and here also the possible number of geometrical isomers are 2. Out of one geometrical isomer, it is optically active only, so you will have one optically active or the optical isomer also for this possible geometrical isomer. So the total stereoisomers will come out to be 2. For example, we did it as COEN3, right? So one geometrical isomer was possible and 2 or basically we can say that one optical isomer was also possible, which was the mirror image of COEN3. So a total of 2. Here also in MAA2B2 or A2, we have found out that geometrical isomers are equal to 2. How? That these two A can be cis to each other. That means the two A's can be 90 degree to each other, or the two A's can be 180 degree to. Right. Now out of these two geometrical isomers, that means in the cis one you will have it as optically active also. So one you have to add for optical isomer also. So this will give you a total of 3 possible number of stereoisomers. Right. And the unsymmetrical ones you can practice. So that's all for today. Okay. I have already made you understand that which one are important from the examination point of view, so you can note them down, right? At least remember the geometrical isomers and the optical isomers for them. Otherwise you can practice or you can learn the table as it is. Okay, so that's all for today. Happy learning to all.